So here's the example, one more example from section 7.7. Graph, oh, mark is bad. F of x is equal to 1 over x where x greater than or equal to 1 is revolved about the x-axis form a solid. This solid has a name. It's called Gabriel's form. Because for one, it looks like a horn. Show that solid has finite volume, but infinite surface area. We're talking about this graph. Y is equal to 1 over x. When x is 1, y is 1. Revolved about the x-axis. So it forms this solid here. Let's get closer. Where this is unbounded. So who remembers how to find the volume of a solid of revolution? I can use a method of disks, right? Here's a partitioning element. When I revolve that, it makes a disk. Formula for the volume using the method of disks is the integral of pi r squared. It's dx, since my rectangle is that way. The radius is going to be the height of that rectangle, which is just the graph 1 over x. And so I'm integrating pi 1 over x all squared dx from 1 to infinity. Agree? So we're just integrating 1 over x squared. We take care of the infinity problem by putting a letter there and taking the limit as that letter goes to infinity. I'll use a big N. What's the integral of 1 over x squared?
Negative 1 over x.
Negative 1 over x. From 1 to n. So I take the limit as n goes to infinity of pi, negative 1 over n minus negative 1 over 1. So as n goes to infinity, 1 over n goes to 0. Agreed? And so this goes to plus 1 times pi. Got pi cubic units of volume. So there's the finite volume. Now for the infinite surface area, we skipped that formula in that section that computes the surface area. So you're just going to have to believe me about this formula being the surface area formula. Surface area of a solid of revolution is 2 pi times the integral from a to b of f of x times the square root of 1 plus f prime of x squared. We skipped this when we were in that section, but we're going to use it now. Our f of x is 1 over x, and our f prime is 1 over x squared. So we're going to integrate 2 pi, the integral from 1 to infinity, 1 over x plus, or I'm sorry, times the square root of 1 plus 1 over x squared squared. Derivative negative 1 over x squared. Yes? So when I square that, I get 1 over x to the 4th plus that 1. So we do what we did before. We write that as x to the 4th over x to the 4th, so that I can write this as a single fraction, x to the 4th plus 1 all over x to the 4th. So far, so good? That x to the 4th on the denominator is all by itself, so I can take the square root of it and get x squared down there. And I'm going to take that x squared down there, and I'm going to multiply it with that x and get the 1 over x cubed here. I don't know that I know how to do that integral. Maybe. I have to do with the double sub. Do I see anything you would try? After we take out that infinity symbol. All right, here's what I'm thinking. Let's see if it works. One, I'm going to take the limit as n goes to infinity, 1 to n. If I were to do a Udu substitution, I'm going to need some version of an x cubed on top, aren't I? So I'm going to do this. Anything illegal? With the x cubed where I needed it, but that means my denominator is now next to the 6. So that I have the original problem, but just a little bit in disguise. So I'm thinking now I can do a double substitution. Take u to be the stuff under the radical sign. Du is 4x cubed dx, so that's going to take care of this guy. I'm going to look at x to the 4th plus 1 is equal to u as u minus 1 is x to the 4th. So the square root of u minus 1 is x squared. Agree? X to the 6th down there in the denominator is x squared cubed. Let me see if this makes an integral that I know how to do. Maybe not. But I'm at least trying something. You're just sitting there like a lump writing down everything I say. Lump, L-U-M-P. Everything, E-D. All right, let me see if I can change this to something I know how to do then. Put this thing out of the way here. Okay, so this is u to the 1/2. X cubed is 1/4 du. And x to the 6th is x squared cubed. So there's my x squared. Didn't help any, did it? Find something? Think out loud with me.
So I was thinking like take x cubed du, or 1/2 du would be x squared. So then so
Right, we definitely don't want that. Definitely don't want to be under the radical. Let's see what happens. Because my Pythagorean identities have squares, not fourths. I don't x to the 4th plus 1. Saying x squared squared would still give me a tangent to the 4th. Right? So what are you saying? Take x squared to be a tan theta? What the heck? Let's give it a shot. Let's give it a shot because I didn't get anywhere. All right, so forget this step. Maybe, let me leave that there for a minute. This isn't going to work. I think I just found the bonus on your problem. Let x squared be tangent of theta. 2x dx is secant squared theta d theta. So dx is secant squared theta d theta over 2x. So x is just going to be the square root of tangent of theta. All right, let's substitute that in up here. So x to the fourth is going to be tan squared theta plus 1. Dx, the secant squared theta over 2 square root of tan theta. D theta. That x cubed down there is the tangent of theta to the 3/2 power. Follow any of that? So try to lose anything. X squared is tangent theta, tan squared theta plus 1 dx. Is 2x dx is secant squared theta d theta. Solve for dx, put 2x under that. X is a squared tangent of theta. So there's that. And x cubed would be the tangent of theta to the 3/2. I think that's okay. So tangent squared theta plus 1 is supposed to be under the radical sign. That's what I forgot. Tangent squared theta plus 1 is secant squared. This is tangent to the 3/2 times tangent to the 1/2. So that's tangent to the 4/2 or tangent squared. This too, I'm going to pull out front. So I got a secant cubed over a tangent squared. I think we can do this. We go to sines and cosines. Secant is 1 over cosine, so secant cubed is 1 over cosine cubed. Tangent squared will be sine squared over cosine squared. This will work. Out above. All right, secant cubed is 1 over the cosine of theta cubed. Tangent squared is sine squared over cosine squared. Oh, maybe. Flip and multiply. Oh, I don't know. I don't know. That gives me a cosine on the bottom. Something left me a cosine on the top. Can't leave that one either. Okay, we're going to figure that one out between now and next time. That looked like it had promise. Sunny beaches. All right, I'll work on that later today, and then I'll get back to you on this on Wednesday. Darn.
Is this Gabriel's smartphone? Something that sounds like we could look at?
We could, but we should figure out how to do some hippos. You can see why we skipped the surface area formula. There's very few things that we can integrate. And there's a much easier formula for when you get to your calculus 3. And you can parameterize the curve and do this with vector calculus. Okay, but I'll come back. I'll come back and look at that. That looked like it was going to work, though. That was pretty good thinking. Okay, let me see what you think about section 8.1. We're skipping two sections in chapter 7. We skipped section 7.6 and we skipped section 7.8. Section 7.6 was about differential equations. You'll get that in your 3350 class. Section 7.8 talks about a class of functions called hyperbolic trig functions. But the hyperbolic trig functions are just linear combinations of e to the x and e to the negative x. So all the calculus that you can do, derivatives, antiderivatives, and even the hyperbolic trig identities are because of the properties of e to the x and e to the negative x. So I think you can live happy, productive lives without specifically sitting down and looking at the hyperbolic functions. I mean, I think I have. I've probably worked with hyperbolic functions maybe twice in my life. Once was in my calculus 2 class. So I'm not going to cover that. Let's go on to chapter 8. If somebody else can integrate this thing before I can, send it to me. I'll think about rewarding you somehow. Put an ice cream cone or something. That's our challenge problem for next class. Okay, in section 8.1, we're going to look at sequences. When you start counting, you're forming a sequence of counting numbers. 1, 2, 3, 4, 5, 6. That's a sequence. List of numbers or symbols that have some sort of pattern. So here are some examples of sequences. 1, 4, 7, 10, ... Goes on forever. I ask you for the next 3 terms of this sequence. Could you tell me what they would be? 13, 16, 19. This is an example of an arithmetic sequence. To move from one term to the other, I'm always adding 3. The arithmetic sequence is one in which we add a fixed number to get to the next term. Here's a sequence: 8, 4, 2, 1. What's the next term? 1/2, 1/4, 1/8. This is an example of a geometric sequence. Multiply by a fixed number. Here we're multiplying by a half to get to the next term. Not all sequences have names. I thought I'd show you the ones with names. Here's a sequence: 1, 0, 1, 1, 0. Let's make put a comma there. 1, 1, 1, 0, 1, 1, 1, 1, 0. So I'm just sticking a 0 in. Oops. Yep. 1, 1, 2 1s, 3 1s, 4 1s, and I'd have 5 1s and then a 0, 6 1s and then a 0, and so on. So those are all examples of sequence. The last one doesn't have any fancy name to it. I just made it up. But a sequence is a list of numbers. In general, I'll write a sequence like this. I'm going to use subscripted lowercase letters of the alphabet to denote the terms of a sequence. It's going to be an infinite sequence. So somewhere out here, I might come to a term that I denote as A n. And the term right before it would be a n minus 1. Term right after would be a n plus 1, and so on. Where those are real numbers, and the subscript tells me the position that the number is in. And when we describe this sequence, I'll use these cute little brackets here. And then I'll put the general formula for the term in there. The mathematical definition is that a sequence is a rule, a pairing between the counting numbers, which are the subscripts, and whatever number that goes into that position. So if my counting number is 1, it pairs it to the value A1. The counting number is 5, it pairs it to the value of A5. So let's see, I want you to write out first 5 terms of the sequence defined by general formula There's the rule that describes it. Sequence of numbers formed by taking n divided by n plus 1. Where n is a counting number. So my first counting number is 1. When n is 1, the first term in my sequence is 1 over 2. Now it's your turn. What's the next term in the sequence?
2/3.
2/3. Next one?
4/5.
And then it goes on forever and ever and ever and ever. What's the 1,000th term?
1,000 over 1,000.
1,000 over 1,001. Here's a sequence for you. Write out the first 5 terms. First 5 terms of -1 to the n. What's the first one?
-1, 1. -1, 1, 8.
Okay. Okay. We can think of a sequence as being plot in the plane where these are the counting numbers and the y-axis gives whatever numbers in that slot. So if I just 1, 2, 3, 4, 5, if I just plotted these, if this is 1, then my first point is at 1/2. The next one is at 2/3. So that's a little bit taller. The next one is at 3/4, so that's a little bit taller. And 4/5. 5/6. Will that sequence of numbers ever escape the roof put onto it by 1? This, but it'll get real darn close to it, won't it? If I try to plot 1,000 divided by 1,001, that's real close to 1. If you have a sequence of values that has a limit, then we say that that sequence converges to that limit. This particular sequence converges to 1. Sequence converges if it has a limit. As my counter goes to infinity. So we can see if I take the limit of that expression in here, the limit as n goes to infinity of n over n plus 1. Remember what we talked about? If the degree on top is the same as the degree on the bottom, the limit is the ratio of the coefficients. The ratio of the coefficients of the n would be give me 1 over 1. Or if you did L'Hopital's rule, you'd still get 1. So this is an example of a sequence that converges. This is an example of a sequence that does not converge. If it does not converge, it's said to diverge. If I were to plot this sequence, it's either going to take on a value of 1 or -1. It's on a value of 1 for the first term, or -1 for the first term, 1 for the second. All the odd terms would be at negatives. All the even terms would be at positives. But as n goes to infinity, I don't have a value of the limit. The limit, as n goes to infinity of -1 to the n, does not exist because it oscillates back and forth. Determine if given sequence converges or diverges if it converges, give its value. Give the value of the limit. If it converges, give its limit. I'm going to give you the general term. So that looks like the list of numbers: e to the -1, e to the -2, e to the -3, e to the -4, and so on. Does this limit exist? If it does, what is its value? It does converge to 0 because this is the same as taking this limit right? So if I think of n being infinitely large, this gets big real quick. And so this whole fraction goes to 0. out sequence's general term is n to the fourth plus 3n cubed minus 1 divided by 4n plus 5n to the fourth.
Compare this to 150.
How'd you get that so fast? Let's in on the secret.
I just looked at the highest coefficient.
The degree on top at its highest is 4. The degree on bottom at its highest is 4. When the degree on top is the same as the degree on the bottom, you just get the ratio of the coefficients. That's what would happen if you did L'Hopital's rule 4 times. You'd end up with a multiple of the ratio of the coefficients. So here, if the degree on top is the same as the degree on the bottom, you get the ratio of the coefficients. What happens if the degree on the bottom is bigger than the degree on top?
Close to 0.
That's right. If it has a polynomial type behavior, the degree on bottom is bigger than the degree on the top, bottom heavy, so the denominator grows faster than the numerator, which means the fraction will go to 0. And if the degree on top is the larger one,
Infinity.
then it grows without bound, right? So if you have things that have powers on them, then you can just kind of look at the ratio of the powers. Remember all that from Cal 1? Okay, what about the sequence? Take the square root of n squared plus 5n minus n. Square root of n squared plus 5n minus n. We saw this a little bit earlier in our example that had the logarithms. All of these n's are in the numerator, so as n gets large, so do those expressions. So this first term gets infinitely large, so does this, but they're being subtracted. So this has the indeterminate form of infinity minus infinity. Not an appropriate indeterminate form for L'Hopital's rule, but is an indeterminate form that says, if you want to compute this limit, you got to do some more stuff to it. So one of the things we know about L'Hopital's rule, what does anybody know about L'Hopital's rule? What does L'Hopital's rule apply toward?
Fraction.
Not just any fraction, fractions that have the indeterminate form of 0 over 0 or infinity over infinity. So L'Hopital's rule Doesn't have to necessarily be limits to infinity, it could be limits to anywhere. In this section, we're looking at limits to infinity. Says that if the limit as n goes to infinity of f of x over g of x has the form 0 over 0 or infinity over infinity, then try taking the limit as n goes to infinity of f prime of x over g prime of x. If this limit exists and is finite, then that's the limit of this thing. If this limit doesn't exist or is infinite, then that's the limit of this thing. So the behavior or the ratio of the derivatives gives you the same thing as the limit of the functions themselves. Well, I mentioned that, and we don't even have a fraction. So how on earth does what I say here apply to something that doesn't even look like a fraction?
Can we make it a fraction?
We can make it a fraction, but it still has infinity minus infinity over 1. Can you make it a better fraction than I did?
Multiply with the conjugate.
Multiply that by the conjugate. There's a standard trick. The conjugate is that same numerator, but with a plus sign between the two terms. So we can take the square root of n squared plus 5n minus n, write it over 1, multiply top and bottom by the square root of n squared plus 5n plus n. Then we'll try to take the limit in our new reduced expression. So my denominator is just going to be that single term. What happens when you FOIL out the top? First times first, first times second, second times first, second times second.
5.
First times the first gets rid of the radical side. The first times the second is the same as the second times the first, but opposite in sign. So they'll add each other out. And then the second one times the second one gives me a minus n squared. So the n squareds are gone, and we have this thing, 5n over the square root of n squared plus 5n plus n. So I'm going to go back over here and write that this limit is equal to the limit as n goes to infinity of 5n divided by square root of n squared plus 5n plus n. Did that help any? It does have a fraction. It does have the form infinity over infinity. But I know from experience that L'Hopital's rule doesn't work when you have a term with a square root and a term without a square root in the same denominator. But I can get this by eyeballing it. I use my good eye. Remember how to take that limit without doing any more algebra? So what's this behave like? What's the highest power of n here?
1.
Just n to the first, right? Because that behaves like n squared over the square root sum. So that behaves like a power of n, that behaves like a power of n, and so does that. So we should get the ratio of the coefficients. So I should get a 5 here, square root of 1 here, and a plus 1 here. So I get a 5 over 1 plus 1, this limit this 5 has. But you kind of remember it now, right? Then we had another sequence that you may kind of remember. remembers taking limits of stuff that look like that? Say it again? One of the steps is that. It's got a lot more steps than we have time for. One over infinity goes to 0. So the step in the parentheses behaves as 1. Then the exponent is going to infinity. So this has an indeterminate form of 1 to the infinity. And that was an indeterminate form in which we used a logarithm. We said, let's pretend that we know this has a limit of L. And let's try to solve that equation for L. But I can get this exponent to come down by taking the natural log of both sides. And I can move the natural log inside the limit. And I chose to take the natural log because the logarithm has a property that the logarithm of a base to a power can be written as that power times the logarithm of the base. And I think the limit as n goes to infinity. So that's the limit as n goes to infinity of n times the natural log of n is equal to the natural log of L. As n goes to infinity, this n goes to infinity. This 1 over n goes to 0, so this behaves like the natural log of 1, which is 0. That's another indeterminate form. Am I bringing back any memories? What do you do when you have that indeterminate form? Take one of your factors and put its reciprocal in the bottom. I'm going to take the n. Multiplying by n is equivalent to dividing by 1 over n. And now it has the form of 0 divided by 0. And I can do L'Hopital's rule. So take the derivative of the top and divide it by the derivative of the bottom. Here's the derivative of the top, derivative of the log. 1 over u. Now go inside. And there's the u prime. Derivative of the bottom gives me another one of those. And I'm going to cancel with that one on the top. So these terms cancel. We take the limit as n goes to infinity with what's left. This is the only term affected by n that's in the denominator, so that term goes to 0. And all that's left is 1. The natural log of the limit is 1. That means the limit is e to the 1. So this particular sequence of numbers converges to the number e. All right, so this section, you have to refresh your memory on how to compute limits. We'll go back and look at that section on L'Hopital's rule. We'll try some more limits on Wednesday, and then we'll talk about what I plan to put on your test. Okay? I've got web work open for section. Oh, I don't know. Did I
7.
open it?
7.
See, I worked over the weekend. Questions, anybody at home? That one comes from the derivative of what's inside,
Oh, okay.
and it cancels with the one on the bottom.
That makes sense. All right, thank you.
Thank you.
Excellent.
Thank you.